In the last lecture, we were talking about concept of band absorptance, and we defined band absorptance AB as integral over the band of the absorptivity within the band, and this has to be integrated over the band. And we pointed out that the band absorptance is a function of the partial pressure of the absorbing gas times the length scale, line structure parameter, and the gas temperature. This is called the pressure path length. This is the line width by line spacing, which is called the line structure parameter. Another thing, of course, is gas temperature. So, this quantity, the band absorptance data, is available for many important gases of relevance to engineering, like carbon dioxide, water vapor, carbon monoxide, and so on. And the information for this has to be available for each band of a gas. If you take carbon dioxide, you will have data for the 4.3 micron band, the 2.7 micron band, and so on. So, in the last class, in the last lecture, we had shown how we can evaluate emissivity in absorptive gas based on the, we defined emissivity, the traditional definition which we had already used for solid surfaces, and we said that we integrate over all the bands of the gas, and so this will be nothing but the value of the black body emissive power at the center of the band center, divided by the temperature, and then in the ith band property, depending on the path length of the gas, the line structure parameter of the ith band, and temperature. So, this quantity is what is available for gases like carbon dioxide, water vapor, and so on. And we also argued that for absorptivity, the same definition would be valid, but but the difference between absorptive and emissivity will be really in how we do the weighting. We weight, this is the band center again, but we weight with the temperature of the source from where the radiation is coming. For example, if the source is sun, we will have to look at sun's black body temperature, and then this part is same, this part is a gas property. So, the key point we made was that emissivity was a function of path length, beta I, and temperature, while absorptivity was a function of path length, line structure parameter, gas temperature, and the source temperature. So, this is similar to what we discussed in the case of solid surfaces, that the emissivity depends on the temperature surface, while absorptivity depends both on the surface temperature and the temperature of radiation from where the source from where radiation is coming. The same thing is valid for gases, except in gases there are two additional parameters to define the gas. One is the amount of gas along the path, and the nature of the structure of this quantity, called the line structure parameter, whether the lines in the vibrating rotation band of the gas are very closely spaced and they are overlapping, so that it does not play any role, or the lines are very far apart and they can be treated independently. Okay. Now, it is good to know how we deal with these situations in limiting cases to understand the nature of this band absorptance. For example, we have defined the band absorptance as integral over the band of 1 minus e to the power of minus a omega L d omega. So, let us consider a simple case where a omega L is much less than 1, what we would call as optically thin. There is very little gas, and so the absorption is very small. So, in which case this A B becomes nothing but you approximate e to the power of minus omega L as 1 minus a omega L, because a omega L is small. So, this becomes nothing but delta omega a omega d omega into L. And normally, the way this here has written in terms of length scale the gas, but normal practice is to define an absorption coefficient, which is let me rewrite this. So, this quantity a omega L d omega can be written in terms of integral a omega by rho, the density of the absorbing gas, into rho a L into d omega. So, this is the so called mass absorption coefficient, which we had defined earlier. This is called the path length, and now this path length will have units of kg per square meter. So, amount of matter along a path, okay, and this is a usually called U. So, U can be either rho a L, or sometimes is also terms of pressure path length PAL, and they are related through the ideal gas law. So, finally, we write A B as rho a L, we call it as U, take it out, it is not a function of omega, and then we write this integral over of a omega d omega, and this is strength, you can call it as the band intensity is called. Called S. Okay. So, in the simple limit, in the linear limit, you can see that the band absorptance is nothing but band intensity multiplied by the path length. And so, this is a useful result. The next thing we will take an example in which, for simplicity, let us assume the band contains only one line for the time being, okay. And if the one line, we know that the absorption coefficient of that line can be written in terms of the intensity of the jth line times the B, the line width, so this is the Lorentz line. So, imagine you have a single Lorentz line and you want to integrate and find out what is the absorptance due to the single Lorentz line. Then your A B for a single Lorentz line, let us call it A right now, this is not a band, this is only a line, absorbed on a single line will be nothing but this over omega 1 minus e to the power of minus S j, we will just call it S for the time being, because we are not looking at right now, S by y b omega minus omega 0 squared plus b squared into u, okay, where u is the path length. Now, suppose line width is very small. The line width of this line happens to be very, very small. That is, in most of your integration, we believe that this is much greater than b square. Then we neglect this term, it does not contribute much. Then this integration can be performed fairly easily, and you get the following result, which is a is equal to 2 square root of b u, and this is known as the square root limit. So, if there is a single line in the band and the line width is very, very small, then you get a result which shows that. So, the condition for this is S u by b is much greater than 1. So, under this condition, you have the square root limit, and so this is a useful information to have, that you can be linear limit if the path length is very, very small, or if the line width is very small, then you can be in the square root limit, and water vapor typically shows behavior which is equivalent to a square root limit. So, this information is useful to determine how you will fit data from experimental data that is available, how they can be fitted for the actual situation. Now, the next step we want to do is to go a little more ambitious and look at more than one line. So, let us now look at extend this is called the Alsacer band model. So, in the Alsacer band model, the aim was to ask if there are large number of identical lines in the spectra. Let me just show the example of an. So, this is, let us go back to our basics now. We saw that absorption gases is through individual lines in the vibration band, but these lines get broadened because of collisions or because of Doppler broadening, and hence the calculation of absorption in gases very much demands that we should know the nature of the line structure. We need to know whether the lines are very far apart or the lines are strongly overlapping. These things play a very important role in the calculation of the absorption by gases. Now, we just considered a single line which, because of collisions, underwent a broadening, and the width was here alpha L, nu 0 the center of the line, and this width of the line depends linearly on the pressure, total pressure of the gas, which determines how many collisions there are. It also depends on temperature, because that determines in some sense the density of the gas also. So, it depends inversely on the square temperature, and you can see that when you are dealing with gases at very high temperature, the line width can be quite small, and when you are dealing with gases at very high total pressure, like inside the diesel engine, then you can have very large line width. So, line width can vary a lot depending on whether you are dealing with a high pressure radiation heat transfer or a low pressure high temperature radiation heat transfer. So, that is an important thing. That is why we have to look at different possibilities. Now, here we show the difference in the line width and the structure of the line, the difference between this one, which is the Doppler broadening, which is exponentially decaying, which we saw, along with Lorentz broadening, which is here, which is goes down as 1 over 1 plus nu squared, and V is a wide function, which is a combination of Doppler and Lorentz. Void follows essentially the width of the. So, what happens is this follows the shape of the Doppler broadening in the center, but as the Doppler broadening effects go down, it takes over and follows the Lorentz broadening shape. Okay. Now, we come to how to. So, the simplest model that Elsasser proposed is having a series of lines of identical height, identical spacing. This is of course somewhat ideal. No real absorption band of a gas shows this kind of structure, but it is very very useful and very illuminating to do this analysis, because it is simple and analytical experiment can be obtained. Of course, you will see later that real. So, this is the exercise you want to do, look at lines which are equally spaced and infinitely both extent, but real world of course is somewhat different. Real world we will have line spacing and height varying a lot. So, in many complex gases like water vapor, this almost looks random, and so people use random or statistical models, but the simpler model is really one using the Elsasser's idea of very simple, because that mainly illustrates the basic features of this thing. So, look at the absorption coefficient, which is a function of the line intensity, line width, and here line spacing is equal. There are n lines along the this one, and this is line width. So, you are going to vary the, this is the line spacing here, this delta is spacing with two lines. So, when you integrate this equation over all n, you will get this result. In this result, what you see is that the absorption coefficient is a function of course the line intensity, and this integrates to Sine and Cauchy functions, hyperbolic sine, hyperbolic cos, and where the function beta is the line structure parameter, which is nothing but line width by line spacing, and of course, the frequency, which is now represented in terms of the line spacing. Now, you have to integrate this further. So, we will do that part now. So, we saw that result which is derived. Now, suppose you want to go further in the derivation, and you actually want to derive the emissivity of the gas in Elsasser band. Then you have to write this is 1 by pi minus pi to plus pi of one of these lines, e to the power of minus 2 beta x sine hyperbolic and cos hyperbolic cos minus cos z dz, where x is nothing but s into frequency, or in this case omega by 2 pi the line width, and beta is nothing but 2 pi BBD. This is line structure parameter, this is a non-dimensional frequency. I am sorry, this is Z here, and we are integrating over frequency, and this integration can be done. One can show that from the integration that the emissivity of the Althusser band is nothing but error function times root pi by 2 S by D I am sorry, let me just go back. This is x, I am sorry, this is x here. This in terms of the, this is the path length, this is the line structure, and the frequency integration is already done. So, this in terms of this length x, and in terms of Bessel functions, I 0 x and I 1 x. Now, this result is very useful, because we can now, although this expression is fairly complicated, and although this specimen tabulated in many books, it is good to look at limiting cases, and let us look at what are the limiting cases of the Althusser. One is of course so called weak line, that is when the line absorption is quite path length is very small, then one can show that the mean emissivity of the gas is 1 minus e to the minus S x by d or more. So, this is a very simple result, very close to what you might get for a gray gas. The emissivity I think 1 minus epsilon d, and in the case of strong lines, that is when x is much greater than 1, essentially similar to the optically thick limit we had discussed earlier. This will be simplified to error function square root of line spacing into and finally, if you have a non overlapping line, so in these things you can see that in this limit, in the thin limit, weak line limit, notice that line structure plays no role. But in the strong line limit, line structure is very much there. Because you can see BBD is playing a role there. So, this can be compared with the result we obtained earlier, the square root limit. This is not quite a square root limit, because error function involved here, but has some similarity to the square root limit. Now, if you look at more general analysis now, this is the simpler analysis which in which you use the very simple Elsasser band model, but if you do a more complicated analysis and you look at the conditions of various situations. Let us now look at empirical fits now. So, empirical expressions for absorptance. So, a lot of laboratory measurements have taken place for gases, and band absorptance has been measured in various situations. So, in the limit when the line width by line spacing is much greater than 1 and u is small, as you can expect, the band absorptance goes linearly as the path length. This is your weak limit or optically thin limit. On the other hand, if line width is much greater line spacing, so is overlapping lines, and the path length is much greater than 1, then A by B goes as log u. So, these are the two very important limits that are available in the literature based on actual measurements of band absorbed various gases, that in thin limit they behave like. So, we plot it in a graph of A B with u, you will find a linear variation at this one and a logarithmic. But the main issue is what is happening here when the u is neither too large nor too small. And so, the condition that has been arrived at, if you define beta as pi b by d, essentially a line structure parameter, then if u is in a certain limit between greater than beta, okay, and less than 1 over beta, then a lot of people suggested that A of B then should vary as 2 root u by beta minus beta. This is essentially a square root limit. And that will typically be somewhere in this region, u is not too small and u is not too large, and that is conditioned by this condition that is given here, wherein u is greater than beta, but less than 1 over beta. So, u is in some value neither too large, and then the square root limit operates in this case. So, generally people fit the band absorptance with A or u or this limit, and this is can be widely used. And an example, now suppose you want an expression for absorptance which combines both the linear and the log, combining linear and log limit. You can write A B is equal to A 0 into log 1 plus u. The advantage of this expression is for small u, this will go as this, and for large u it will go as log u. So, this is quite convenient expression, has been used, but note that line structure parameter plays no role. So, this may not be that useful in situations where the line structure is important. So, we want to examine cases where the line structure is important, then you need to look at examples where you have to fit the effective line structure into your into expression. And one example of that can be provided is there are various complicated models available, but let me just give you a simple expression for A of B, which will take into account the line structure parameter. We saw one example of that already, which is A B actually A B is equal to A 0 into. So, this is different from these, there beta play no role. So, essentially you must assume that beta is very large. So, that the lines are so overlapping that the line structure gets smeared out. But if you encounter gases in which line structure is important, then you have to look at expressions of this kind, and we will consider one of these examples in our attempt to use the band absorptance examples in real situations. Now, how do we use this concept of band absorptance in real examples? And so, we will take an example now of radiative equilibrium, in which you consider a gas which has a single vibration rotation band, and then you would like to be able to rewrite the radiative transfer equation that we had obtained, and we will take an example that is relevant to combustion application. And so, let us see how we rewrite our expression for radiative flux in terms of the. So, what is the basic philosophy there? The basic philosophy of this model is that if A is delta integral over omega of e to the power of A omega L d omega 1 minus, then d A I will write a u here, this is convenient this one. So, you can see that from there d A du nothing but delta omega A omega e to the minus A omega u d omega. So, if you look at our expression for Q r integrated over the entire vibration band, you will have of course E b 1 minus E b 2 black body emissive power, that is standard. Then you have used a kernel approximation like we did in the example for quasi-Gray model, same logic we use, integrate from 0 to some distance y, and we have e to the power of b omega and e to the power of b 1 omega. This is the represent gas radiation and radiation of the wall, and then integral over the wave number a omega e to the power of minus 3 by 2 a omega into y minus y tilde. The d by tilde can come out here and d omega can be there. So, this quantity should be recognized as nothing but dA du or dA dy in this case. So, with these definitions and defining a non-dimensional length scale as y by L and non-dimensional path length u as S into P, the maximum path length is S into the particle width of observing gas length scale by the bandwidth, and non-dimensional band absorption as this. If you use these three definitions, then you can rewrite our expression for QR as EB1 minus EB2 plus 3 by 2 A0 U0 and we open the bracket 0 to psi EB omega of psi tilde minus EB1 omega. Then derivative of the band absorptance prime of 3 by 2 u by psi minus psi tilde d psi tilde minus the integral from psi to 1 of EB omega of psi tilde minus EB2, which is a constant, not a function of scale, into derivative of the band absorptance of psi tilde minus psi d psi tilde. So, the standard integral equation that you obtain in this case. And now, let us see how this equation can be solved. Now, if you want to solve this equation, let us take a very simple example just to illustrate the. Suppose you have a heat source which we have done earlier. So, minus dQr dy plus a heat source equal to 0. This is heat released by combustion. Then you can rewrite this whole equation in the large Bottleneck limit, that is for u0 much greater than 1. This is written as psi minus half to 0 to 1 phi of psi tilde d psi tilde psi minus psi tilde, where phi is a non-dimensional temperature profile. So, this is a very interesting experiment for the large path length limit, wherein you do not see any line structure parameter in your expression. You are merely only seeing the role of the logarithmic limit, because in the limit as this we know that the band absorptance goes as a to the power 0 log u. So, derivative of band absorptance is 1 over u, and that is what you are essentially getting here, and the solution to this equation in this limit is a very elegant one, and which has been used, which is the only solution which we have, which is analytical. So, non-diagonal temperature profile will come out as 1 over pi psi into 1 minus psi into square root of that. So, this is an unusual result, very rare result, wherein you got an analytical solution to the temperature profile in a gas having a vibrating rotation band in the limit where the path length is very large, but it is important to recognize that the large path length limit is not similar to optically thick limit. Now, this is because in a non-gray gas, even if the path length is very large, there will always be regions, wavelength regions in which the gas is not going to absorb much radiation. So, radiation will just get through the gas. Now, this looks a bit surprising and may not seem obvious. So, to illustrate this point, we will take one example to we illustrate this with a point which we would like to make here, which is that in this large path length limit, in spite of large path length, the gas will not completely absorb all the radiation. To illustrate this point, I would remind you of the example we had in the last class, in which we looked at the emissivity and absorptivity of carbon dioxide, and we took example of a gas with a total pressure of 1 bar, typical of furnace situation, containing 20% carbon dioxide, 80% nitrogen, length scale of the order of 5 meters, gas temperature of 1500 Kelvin, and a wall temperature of 600 Kelvin. And when we did the calculation last time, we saw that the absorptivity of the gas was around 0.1, 0.41, while the emissivity was 0.18. So, you can see that in spite of a fairly high temperature and fairly large length scale, alpha g, epsilon g do not approach 1. They are quite small, and hence the air is so this neither of this can be thought of as the optically thick limit, in which we saw that in the case of gray gas, it implied essentially the emissivity and absorptivity approaching 1. For example, if we take gray gas, So, emissivity of a gray gas will 1 minus e to the power of minus a l. So, in the thick limit, both alpha g and epsilon g will approach 1, but in real gases that does not happen. And so, that is an example that is worth remembering, that real gases behave substantially different from gray gas, which is a notion which is used in our example, but it is worth remembering that this is not good in the thick limit, because the thick limit the gray gas behavior will not be same as real gases, because real gases do allow radiation to be transmitted. Now, in all the examples done so far, we have relied primarily on empirical data for band absorptance. Now, the question is, how is this calculated? Now, to illustrate that, let us go and look at the problem here. Here we have shown the typical variation of the absorption coefficient in the range 150 to 1510152 centimeter minus 1, at a fairly high pressure for a carbon dioxide band here, and you can see that there are a large number of lines here, and this is a logarithmic scale. So, that the absorption coefficient vary anywhere from around 10 to the power of minus 3.001 to 100. So, you have a huge variation from 0.001 to 100, almost 100,000 is the ratio between this point and this point, and hence you can see then when you do those integrals for radiation calculation, one needs an extremely high resolution in the wave number axis to be able to really capture these peaks, because if you use a very crude step size here, you will not capture these peaks. So, this is a major challenge we face in calculating absorption coefficient of gases, which is that there are large number of lines, hundreds of them, and they go from almost 0 absorption to very large absorption, varying a factor 100,000 in a very short very short scale here. And so, in order to really capture the absorption lines here, you need extremely high resolution, and this is what makes the computation of absorption coefficient or computations in radio transfer very complicated, because of this very large fluctuation in the absorption coefficient. One way to get around this complexity is to recognize the fact that although there is very large fluctuation absorption coefficient with frequency or wave number, the actual frequency in which that line lies is not that critical. If you want to understand why, let us now go back and illustrate this with our example of, we saw that epsilon g is integral over the frequency of 1 minus e to the power of minus a omega L d omega. Okay. And this a omega is fluctuating by factors of 100,000, and remember is multiplied by E b omega at the gas temperature. So, the key thing to understand is this is slowly varying. Function of omega when compared to this. When compared to this function is slowly varying. So, we are going to take this at the center of the line, center of the band, and do only this integration. Okay. And of course, sum over all the bands. So, I will write this as the ith band, I equals 1 to n bands of the gas. If you are doing this integration now, it does not matter where your absorption band is, because this is not varying much, we are taking it out. Therefore, in this integration, the exact location of omega in the wave number place is irrelevant. So, you can go back this one and rearrange this graph. So, this expression you want to calculate, and it is integrating over frequency domain, you integrate over the absorption coefficient domain. You merely ask, let me go back and show you how it is done. So, for example, you take one line here, ask all these locations where absorption current was around 100 or around 10 for example. Then look at location where it is around 1. Find the probability in this band that the absorption coefficient was 20 or 50 or 1 or 10, and once you know that probability, that is the f of k. Probability f of k is a probability that absorption current is equal to k. Okay, the u is the path length. And so, we will show how it looks like. This is now the same data that you saw earlier, written not in the frequency space, but in the probability of occurrence of that absorption coefficient with absorption coefficient. So, absorption coefficient varying all the way from 0.001 to 100 here, and this what is the probability of it occurring. What you must notice very clearly is that the highest probability is for very low absorption coefficient. So, there are a lot of transparent regions in the gas between the lines, lot of transparent region in the gas, and then gradually it comes down to high absorption, but low probability. Notice that this result is very different from this graph. This graph was very noisy, things are going up and down and difficult to integrate. On the other hand, this integration is very simple to do, because this quantity is very smooth, except for little things there, but you can make it look even better if you plot the absorption coefficient as a function of the cumulative probability, which is defined g of k nothing but 0 to k of f of k dk. This is a probability that absorption coefficient lies between 0 and k, g of k, cumulative probability. So, ultimately what you see is that although the real absorption coefficient is a very complex and fluctuating function of the frequency or wave number, if you do not integrate in the wave number space, but desire to integrate in the absorption coefficient space, which we can do, because in the calculation of emissivity absorptivity, the black body function does not vary much in the within the absorption band in comparison to the way the absorption coefficient varies. So, if you take out the black body function out of the integral, the remaining integration can be performed in the space of absorption coefficient, and even better in terms of the cumulative distribution. This is a very smooth function, and this smooth function is shown for two different pressures, low pressure and high pressure, and you can see at high pressure absorption is larger to be expected. And now this integration is very trivial to do, and that is what is finally done. To get the transmittance, you merely integrate in the space of cumulative absorption coefficient function rather than frequency, and this is very easy to do. So, this is called the correlated k method, and this shows how the real function, which was very complicated way, ultimately is made to look both at low pressure and high pressure as a very smooth function. And this is what has made the computation of absorptivity and emissivity very simple, and today most of the calculations are done by this method, and this method is called the correlated K method. So, the correlated K essentially indicates you that we are collecting together absorption coefficient same value together and remapping the absorption coefficient, which was originally a function of frequency. Now, it is made a function of absorption coefficient itself, and that function is much smoother and much easier to calculate, and the accuracy of this calculation has been compared with the best calculation, which is line by line, which is very expensive and tedious, and they have shown that this method is quite accurate. So, most of the data available today is in terms of the correlated K method, because that method is much easier to compute than line by line, but line by line is still a reference data, because that is the exact accurate method that we have, but most of the time you are going to use the data obtained from the correlated K method, and so most of the data available to you will be from the correlated K method. So, we will continue this discussion in the next lecture.